Hello there. So we have understood the basics of current reference and the current mirror so far in our tutorial series. And we have started this another playlist in which we are doing the circuit analysis to brush up our fundamentals and add more insights to what we've covered and what we've understood so far. So I've said initially that, okay, we need current biasing uh, into the when we design an electronic circuit, there are many elements that need a current to be supplied, and there are many elements in the when you design a circuit that also need voltage sources or voltage references into the circuit. So let me add to that. We need current biasing and we need voltage biasing. So we also called as current reference and we also called as voltage reference. So we basically need voltages and currents to bias variety of points in our circuits. So let's say you are designing an operational amplifier or analog to digital converters. So you need a current biasing to bias your transistors and many other components, and you will also need voltage references. So how to generate them, right? So here is your current I that you see here. I am representing it with a constant current source. So when I am saying constant current source, I will say this is my I versus V. So I would say this current that I produce will remain constant irrespective of the voltage across it. It should deliver me a constant current even if the voltage across it changes. So that's the definition of an ideal current reference or current source. So obviously this V plus, if it is changing, which is the power supply, I should still have the I should be constant. It should not have any variations. And also the same story goes for change in temperature, change in loading. So still the I should be constant. So that's the definition of. So there are some specific circuitries that we will explore later to generate this kind of or design this kind of current reference or current source. Same story applies to the voltage bias and voltage reference. So I would need a voltage that will remain constant irrespective of the current that is drawn through it. Okay, I can draw any amount of current and it should still deliver me a constant voltage. So that's the definition of the voltage reference or voltage source. So there are circuits, dedicated circuit to design both of these combination. So here in this circuit, there is an example. I would use, for example, V plus here, and I can use a simple resistor instead of this current source to generate the same current I, because the current that will flow is my I. And then I use the MOSFET as shown, the way exactly it is shown, to bias and do the rest of my circuit processing and signal processing. So I have this one. But the drawback of using R to generate the reference current is that if the voltage changes, for example, the value of current that I will generate using the resistor can be written as, let me write here, the current that I'm going to generate will be this voltage V plus minus the voltage drop across this, which is like this is drain pin, this is gate pin, and this is source, and the drain and gates are shorted. So I will say VGS or divided by R, right? So if R changes, I have change in the I, right? And also if the supply changes, I have change in the I. So that shouldn't be the case. So there are some strategies to design the current sources and the voltage sources which have independence from the load temperatures, and some other systematic errors. So right now, our focus is to help you understand uh, what is the use of this circuit. For example, I have used the current reference, and then this pair of transistor, using this pair of transistor, I have designed current mirror. So this circuit is helping me to mirror the current in M1 into M2. So the condition we have seen before, M1 and M2 are exactly same type, and their voltage is VGS, that is at the gate and the source here. Here also gate and the source. So VGS1 is equal to VGS2, and M1 and M2 are same. That means their length are same, their width are same, their threshold voltages VTH1 is equal to VTH2 are also same. And when such condition happens, I will say ID2 is equal to ID1. And ID2 is nothing but my I out, which is an output current, which is therefore I can say that output current. And ID1 here is equal to I. So I will say I out will be I. So I have managed to mirror this input current into the output transistor, that is M2. Okay, so this is how the current. But now where to use this generated or mirror current, that is ID2 or I out? So the answer is, you have an amplifier, for example, a differential amplifier using two transistors. What you do, a differential amplifier to this transistor, let us say I call it MD1 and this is MD2, and both are NMOS type. So I have applied the voltage V1 to one transistor and the voltage V2 to another transistor. And then obviously here are the loads, resistors RC1 or RC2. And then obviously you have this VDD, that is your power supply. And now the emitter, but there's a MOSFET, so instead of emitter, we would say they are the source terminals, source pins of both the transistors. They are shorted together. And now you need a tail current. So that's the tail of the differential pair. So to bias the tail current, we have such kind of connection. So that's how you generate the input current I, and then you use the current mirror to, for example, give bias the tail current of the differential pair. So that's the use of it. RC1 and RC2 can also be replaced by an active load. So active load is like you use the transistors to just replace the RC1, RC2. We basically use the MOSFET again in the diode connected fashion and the was shown. And instead of RC1 and RC2, you will do. So when we will study the differential amplifier, we can actually understand that. What can you do more? For example, you have, let's say, this is the first stage. Let's say you have another stage. For example, this is an output. So here is your output of the circuit, positive, negative. This is, let's say, V1, VO1, and this is, let's say, VO2. And final output is VO. So which is the differential output. And now let's say you have a single-ended output here that you use to connect to an output stage of the differential amplifier. So here is another differential amplifier. So for example, and again, you have another gain of the transistor, and then you need bias current to this branch also. So what you do, you connect the same, because the now VGS for M1 and M2 are same. Use this generated VGS to apply to another transistor right here, and that becomes, and this is ground, and this is how you have VGS here that biases the another transistor, and that is your ID whatever the name of the transistor. Let's say this is M5 and this is M6. So this will be ID6. That is the. So you see, this is how you use the current mirroring technique to bias, to provide the bias for various branches in your circuit, right? So we'll do the more exact and precise analysis as we progress. So hope you found this video useful. You like this. If you did so, make sure you click the like button, subscribe to our channel, and share with others for wider reach. Till then, stay tuned. Wish you happy learning.